We now start the presentation of module 1 of chapter 10. Though the content of chapter 10 is equivalent to 4 hours of teaching, that is 4 modules, we have decided to present a brief part of it into 2 modules. So, we start the first module. Now, in this chapter, what we are going to do is that we are going to introduce a generalization of the notion of Riemann integral called Riemann-Stieltjes integral. This generalization is done essentially by replacing xk minus xk minus 1, that is delta xk, in the definition of lower and upper sums, or equivalently in the Riemann sum, by delta alpha xk, that is alpha xk minus alpha xk minus 1 for some particular function alpha. In particular, if we take the function alpha as the identity function, then we get the Riemann integral. So, let us go and see the first slide, where the formal definition of Riemann-Stieltjes integral is given. Before giving the formal definition of Riemann-Stieltjes integral, let us try to understand what is the motivation behind this concept. For example, if we consider the problem of finding the moment with respect to the y axis of a distribution of mass over closed interval a x, if m x is the amount of mass over closed interval a x, then it is known that the moment with respect to the y axis is described by the following sum: sigma k equal to 1 to n x k m x k minus m x k minus 1, where m x k minus m x k minus 1 stands for the mass between x k minus 1 and x k. So, in these cases the Riemann-Stieltjes integral comes very handy, because here we are considering a sum sigma k equal to 1 to n x k into delta m x k. In particular, this integral is more used to deal with situations where the function alpha is appropriately chosen to express a finite or infinite sum as a Riemann-Stieltjes integral, and this integral has many applications in physics and mechanics. So, now let us start with the formal definition of Riemann-Stieltjes integral. The definition is quite similar to the definition of Riemann integral. We start with a partition P a equal to x 0 less than x 1 less than x n equal to b of closed interval a b. As always, the set of all possible partitions of closed interval a b is denoted by pi a b. The norm or mesh of the partition P is defined as always to be the length of the largest subintervals of P, and it is denoted by norm P. It is easy to understand that if a partition P dash of closed interval a b is finer than P, that is, it is a refinement of P. In other words, when P is subset of P dash, that is, the number of points in P dash is greater than the number of points in P, obviously norm P dash is less or equal to norm P. The symbol delta alpha k will denote the difference delta alpha k equal to alpha x k minus alpha x k minus 1. So, that we have sigma k equal to 1 to n delta alpha k, this is equal to alpha b minus alpha a. Now, the main definition, let P a equal to x 0 less than x 1 less than x n equal to b be a partition of closed interval a b, and we take an arbitrary point t k from each sub interval closed x k minus 1 x k for each k equal to 1 to n. Now, a sum of the form S P f alpha, which is equal to sigma k equal to 1 to n f t k delta alpha k, this is called a Riemann-Stieltjes sum of f with respect to the function alpha. So, see that if we take alpha as the identity function, then we have sigma k equal to 1 to n f t k into x k minus x k minus 1, which is our known Riemann sum of f corresponding to the partition P. We say that the function f is Riemann-Stieltjes integrable with respect to the function alpha on closed interval a b if we can find a real number capital A which has the property that for any given epsilon greater than 0 arbitrarily small, there is a partition P epsilon of closed interval a b such that for every partition P which is finer than P epsilon and for any choice of the points t k in closed interval x k minus 1 x k, we have mod S P f alpha minus capital A less than epsilon. So, the definition is exactly similar to the definition of Riemann integral. The only difference is that here we are taking another function alpha. This number capital A can be shown to be uniquely determined, and it is denoted by the symbol integral a to b f d alpha. F is called the integrand and The function alpha is referred as integrator respectively, and if f is Riemann Stieltjes integrable with respect to the function alpha, then we say that f belongs to R alpha. The basic properties of Riemann Stieltjes integral are exactly similar to the basic properties of Riemann integral with some additional properties, and the proofs are not very difficult. So, we just state the results without going into the details of the proofs. The first property is linearity property, which states that if f and g are Riemann Stieltjes integrable with respect to a function alpha on closed interval a b, then for any two real numbers c d, the function Cf plus dg is also Riemann Stieltjes integrable with respect to the function alpha on closed interval a b, and integral a to b Cf plus dg d alpha, this is equal to C integral a to b f d alpha plus d into integral a to b g d alpha. In other words, the collection of all Riemann Stieltjes integrable functions on closed interval a b with respect to a fixed integrator alpha form a vector space. The second property is that if f is Riemann Stieltjes integrable with respect to integrator alpha, and at the same time f is Riemann Stieltjes integrable with respect to another integrator beta on closed interval a b, then f is Riemann Stieltjes integrable on closed interval a b with respect to the integrator C1 alpha plus C2 beta for any C1 and C2 belonging to R, and further integral a to b f d C1 alpha plus C2 beta is equal to C1 integral a to b f d alpha plus C2 integral a to b g d beta. The next property states that if we take an intermediate point C from open interval a b, that is a less than c less than b, and if we consider the three Riemann Stieltjes integrals, integral a to b f d alpha, integral a to c f d alpha, and integral c to b f d alpha, then the existence of any two of these three integrals implies the existence of the third integral, and we have integral a to b f d alpha is equal to integral a to c f d alpha plus integral c to b f d alpha. Now, let us prove one of the most important theorems for Riemann-Stieltjes integral. Let f be Riemann-Stieltjes integrable with respect to the integrator alpha on closed interval a b, where the integrator alpha is chosen in such a way that alpha has a continuous derivative alpha dash on closed interval a b. Then the Riemann integral a to b f x alpha dash x dx exists, and integral a to b f x d alpha is equal to integral a to b f x alpha dash x dx. So, this shows that for some particular choice of the integrator alpha, the Riemann-Stieltjes integral a to b f d alpha is nothing but the Riemann integral of the product function of f and alpha dash in closed interval a b. We start the proof. For a given partition P, which is given by a equal to x 0 less than x 1 less than x n equal to b of closed interval a b, and any arbitrary point t k chosen from the sub interval closed x k minus 1 x k for every k equal to 1 to n. Let us consider the Riemann sum S P f alpha dash, which is given by sigma k equal to 1 to n f t k alpha dash t k delta x k, where delta x k is x k minus x k minus 1. Now, for the same partition P and the choice of points t k, let us consider the Riemann-Stieltjes sum S P alpha, which is given by sigma k equal to 1 to n f t k delta alpha k, that is alpha x k minus alpha x k minus 1. Now, if we apply the mean value theorem on the function alpha in the interval closed x k minus 1 x k, because by our assumption alpha dash exists in closed interval a b. So, we get delta alpha k, that is alpha x k minus alpha x k minus 1 is equal to alpha dash c k into delta x k, that is x k minus x k minus 1 for some intermediate point c k coming from the open interval x k minus 1 x k. So, if we take the difference, S P F alpha minus S P F alpha dash, this is equal to sigma k equal to 1 to n f t k delta alpha k minus sigma k equal to 1 to n f t k alpha dash t k into delta x k, and we can take f t k common, so that the sum becomes sigma k equal to 1 to n f t k bracket alpha dash c k minus alpha dash t k into delta x k. Now, by our assumption, the function f is bounded. So, we can find a positive real number capital M such that mod f x is less or equal to capital M. Now, since alpha dash is continuous on closed interval a b, so from the property of continuous functions on closed interval a b, we know that it is also uniformly continuous on the closed interval a b. So, using the criteria of uniform continuity for the function alpha dash, for every epsilon greater than 0, we can find a delta greater than 0 such that mod alpha dash x minus alpha dash y is less than epsilon by 2 capital M into b minus a whenever the points x and y are chosen from closed interval a b in such a way that mod x minus y is less than delta. Now, choose a partition p epsilon dash with norm p epsilon dash less than delta. Then observe that for any refinement p of p epsilon dash, we have mod alpha dash c k minus alpha dash t k less than epsilon by 2 capital M into b minus a, and this shows that mod S P F alpha minus S P F alpha dash is less than epsilon by 2. Again, observe that the function f is remains tilde integrable with respect to the integrator alpha on closed interval a b. So, from that criteria we can find another partition p double dash epsilon such that for any partition p which is finer than p double dash epsilon, we have mod S P F alpha minus integral a to b f d alpha is less than epsilon by 2. So, we have now two partitions p dash epsilon and p double dash epsilon for the same epsilon greater than 0 given. So, choosing p epsilon as the refinement of both the partitions, that is taking P epsilon as P epsilon dash union P double dash epsilon, we see that when we take any partition P which is finer than P epsilon, we have mod S P f alpha dash minus integral a to b f d alpha, this is less than epsilon. And since epsilon greater than 0 is arbitrary, so this proves our assertion that f alpha dash is Riemann integrable, and at the same time the Riemann integral of f alpha dash over the interval a b is equal to integral a to b f d alpha. Now, we go to another result without going into its proof. Let a less than c less than b, define the function alpha in this way: alpha x takes the value alpha of a if a less or equal to x less than c, and it takes the constant value alpha b in the complement of that interval, that is when c less or equal to x less than b, and further assume that at least one of the functions f and alpha is continuous from the left at c, and at least one is continuous from the right at c. Then the function f is Riemann-Stieltjes integrable with respect to alpha on closed interval a b, and integral a to b f d alpha can be obtained by this number f c into alpha c plus minus alpha c minus. So, to summarize, what we have done in this module is that we have introduced the definition of Riemann-Stieltjes integral, which is a generalization of the notion of Riemann integral, where delta x k, which is x k minus x k minus 1 in the definition of Riemann sum, is replaced by delta alpha k, that is alpha x k minus alpha x k minus 1. And in particular, if we take alpha as the identity function, then we get the definition of Riemann integral from the definition of Riemann-Stieltjes integral. Finally, we have proved a important result showing that if the integrator alpha is such that alpha dash is continuous and bounded in closed interval a b, then f alpha dash is Riemann integrable on closed interval a b, and the Riemann-Stieltjes integral of f corresponding to the integrator alpha is equal to the Riemann integral of f alpha dash over closed interval a b. And with this comment, we end this module.